I'm going to talk about scalable exploration through fast uncertainty estimation for reinforcement learning. My name is Liyingru Li, and I'm working with Tom Luo and from Chinese University, Hong Kong, Shenzhen. I would first talk about the motivation, the existing solution and limitations, and our contributions, the HyperAgent. Reinforcement learning is about an agent interacting with the environment sequentially. The agent will observe the state and take the action according to its experience, and then the environment will return the next state. The agent will use the history experience to adapt its policy such that it can maximize the long-term expected reward. So here, the interactive experience will be accumulated in the data set D. Okay. And the challenge to deploy reinforcement learning algorithm in real-world applications typically depends on the environment and also the agent side. For the environment, the contemporary application involves large state space because of some unstructured inputs, for example, languages, visions, or even audios. So the state space is exponentially large in such applications. And also for the history data set, since this is an interactive process, so the data or the experience will be increasingly large as this agent is continuously interact in the environment. And the agent itself has resource constraints. For example, their computation power and memory is bounded. Their resources is bounded. Okay, so the algorithm should be with bounded per step computation complexity. And also for many applications, the interaction to acquire new information, such data collection process has limited budgets. For example, in a contemporary very important problem, which is essentially deployed in many social network platforms, for example, Facebook, Twitter, X, or just Instagrams, and also even for GPT, they have their own content moderation systems. So in each time step, this is an online production environment. Okay, in each time index, the posts, which here is the context, will be observed by the AI moderation system. We consider it as an agent. Okay, and all other component is environment we consider here. So the AI moderation system will help to classify which context should be automatically removed because it is already known as very harmful or inappropriate information there in the content, or it is uncertain about that, and then it will put it into human review. So the problem here is that first, the context here or the post here is with the unstructured input, for example, natural language, and also this every seconds there's a huge amount of post here, but the human reviewer is very limited compared to the number of posts. So this faces the limited data collection budgets because human reviewer will review such content and provide the label of the content, whether it is aligned with human value or not, to improve the future capability of this AI moderation system. Okay. So this is the online decision-making process, which can be modeled as some kind of contextual bandit problem. Um, but essentially, this is a very appropriate example that uh, exemplifies the challenge I mentioned about. So the problem here is that can we design scalable and data efficient our algorithms under resource constraints? So the first one is about scalability, which means that even when this kind of large foundation model are used for processing such unstructured inputs such as language and or visions in this process, it still needs a bounded per step computation because it has to be a real-time decision because this is very critical real-time online system. Okay. And also for data efficiency issue, because of this human reviewer is limited, so we need to actually this AI moderation system should be notice that it will defer such content to human review such that it can improve most give the most improvement of the agent's future capability. So this is a data efficiency issue. So it is measured by some kind of measure in theoretical measure in regret. Okay, existing solutions and their limitations. The history of developing reinforcement learning algorithm is about scaling up. For example, even using deep neural networks as approximation or large foundation model as approximation, it will handle this dependence issue on the state space. And for the development of temporal difference or Q learning, it will be a incremental update and that will be dealing with the per step issue in complexity in terms of no dependence, in terms of the dependence on the number of data points in the history. So this two basically makes this algorithm scalable. Okay, so this is a kind of scaling up process of reinforcement learning, and this is about computation. However, this kind of algorithms are not sample efficient in terms of the data collection budgets, right? And for example, there's some advancements for sample efficient deep RL, but this kind of algorithms are really adding a huge amount of tuning heuristics or complex components, and this is not deploy efficient. And also, these algorithms, even in the last year, this kind of state of the art, bigger, better, faster, still use epsilon greedy, which is probably inefficient in terms of some environments. Okay. And there's another line of work by starting from Thompson in the 30s, and to deal with such a sample efficiency issue or data efficiency issue in terms of sequential decision process. And it is measured by sublinear regret. Okay. Sequential decision making under uncertainty requires the uncertainty estimation. The famous algorithm or scheme called posterior sampling or Thompson sampling basically estimate uncertainty in a Bayesian view such that it will update its posterior according to a prior and also the current knowledge under the data set it observes. It will update it as a posterior and then sample a model from posterior and act accordingly, greedily according to this sampled model. And this is basically a scheme of posterior sampling. But this kind of process requires conjugate property to update this posterior in a computationally tractable way. So this kind of concerning estimation requires conjugacy. and is only feasible in very simple environment, for example, tabular MDP and also linear Gaussian bandit. And for scaling up such posterior sampling strategy, we require scalable method for uncertainty estimation. Even for linear function approximation, it is not tractable for posterior sampling, exact posterior sampling. And for some approximate way to do posterior sampling, their algorithm, for example, randomized least square value iteration and Langevin-based method, their computation complexity will grow unbounded, actually grow linearly in terms of the number of episodes or number of time steps. So it is also not acceptable for bounded resources in the agents, right? And same issue observes in the optimism-based algorithms. There is exceptional, interesting one that tries to tackle such a problem that is called ensemble sampling. It maintains a set of plausible models, each one incrementally updated, and in each step or in each episode is going to be uniformly sampled from the set of ensembles and then act greedy according to the sampled ensembles. So this ensemble sampling basically inherent from the incremental update, and it wants to approximate some kind of posterior according to their claim. However, there is no rigorous theoretical understanding about such behavior in terms of both statistical complexity and also computation complexity. So it seems like this two lines of work are diverging, and in our work we try to bridge the theory, which in terms of regret and also in terms of about the practice in terms of computation scaling up. So this is our goal. Then we propose the HyperAgent algorithm. The HyperAgent algorithm needs only one additional component, hypermodel, to double DQN, and it is compatible for this kind of hypermodel I'll mention later will be compatible for every almost every feed-forward DQN, deep neural nets. So it can be easily to deploy, and is inherent from DQN scalability. So it's still scalable, and we don't have such many tuning components. Okay, so no prior replay, no dueling, no distributional RL, no harder reset, no self prediction. We don't have larger network, and we don't have many tricks to tune the hyperparameters. So basically, we use the DQN and also this hypermodel. This is for practitioners. It is simple. Okay. And the achievements is that to achieve the human level performance in entire benchmarks, we only use 50% of data compared with double DQ, and also we use 5% of model parameters compared with BBF, which is the state of the art last year by DeepMind. And for ensemble methods, they only achieve 0.2 IQM, which is basically 1 IQM is human level performance. So they only achieve 0.2 IQM under the same interaction data as ours, agent. And they use double the parameters there. And here the parameter in this kind of problems and structures is proportion to the per step computation costs. And for the deep C benchmarks that measures the deep exploration behavior, our HyperAgent is the first one to achieve the linear scaling empirically according to this, because this problem has is optimal scaling with the environments about how many episodes needs to learn is linear scaling in this kind of environment. And previous EN and ensemble method cannot achieve such linear scaling. Even with the size with 60, they are failing. All other method are failing. Okay, all the method fails. And also for hard exploration in Atari games, the blue line is our algorithm that surpasses Rainbow and surpasses Ensemble, and also surpasses a lot in terms of the recent proposed Langevin-based method in this year iClear paper, Langevin, and also supports in a huge amount of variation approximation of posterior. So empirically, it works very well in deep RL, and also the mentioned contemporary significant problem in every social network or every online platform, digital platforms. The content moderation process in online setup is essentially a lot online automatic decision-making problem inherently. So it needs the collaboration between humans and AI. However, the human resources, the human feedback budget is limited. So our algorithm basically saved the human labeling efforts by tenfold if compared with this greedy method that is considered no uncertainty in terms of the which content will be moderated by a human. Okay, so it achieves higher detection accuracy in terms of detect which content is harmful or not. And here we augment our HyperAgent with GPT-2. Compare with the random initialized GPT-2, the pre-trained GPT-2 with our HyperAgent actually is better in initial. It solves the cold start problem using foundation models augmentation. Okay. Theoretically, we prove that with the same algorithmic framework, the only difference is that we put the feature mapping into one-hot mapping in tabular RL. It is a tabular representation of our algorithm, but the update rule in the algorithm is the same. Then we prove that the per step computation is logarithmic in K. And among this kind of randomized algorithms, and for the regret, it matches the PSRL and RSBI. The ensemble method, although it's also incremental, but it doesn't have any, at least for now, is not known in terms of the computation regret. So this is a milestone in terms of the theory. And also for contextual bandits, the ensemble sampling and Langevin method, they use the computation per step linearly in T, which is the time steps. And our method only scale logarithmically in T. Okay, so this is an exponential improvement in the linear contextual benchmarks. And also for the regret bound, it matches the exact Thompson sampling. So this is a significant advancement that closes the gap in the theory for scalable and randomized exploration. Okay, and also this works for various setup for decision sets. The key mechanism is that we provide a approximate posterior sampling algorithm based on hypermodel and index sampling schemes, such that it achieves data efficient exploration. To prove such mechanism, we give a key lemma that such that HyperAgent is actually an incremental posterior approximation algorithm that without using any conjugate property. So this is the key insight. And also, to emphasize this incremental process, every incremental update only needs logarithmic computation complexity. So this process is computationally scalable. Okay, so it is a scalable way to do uncertainty estimation in terms of Bayesian view of uncertainty, that is the posterior update. To prove this key lemma, we provide fundamentally novel tools for dealing with non-IID data that is inherently the nature of sequential decision making. So we provide the first probability tool for sequential random projection, which is a non-trivial martingale extension of Johnson-Lindner stress. And for statics data, we also have some new results, new theoretical results to deal with the spherical random projection matrix. Okay, what is HyperAgent? Before HyperAgent, we will introduce the hypermodel that is basically introduced by in the Van Roy's group, actually, at that time, and also is related to epistemic neural nets. We will mention something different than their hypermodel and the original hypermodel, and also the ENN. And basically, this is also our work based on hypermodel. Anyhow, so this hypermodel is a parametric function that takes the index from reference distribution. You can think of a fixed Gaussian distribution in low dimension, and it transforms the x input and the index to a posterior predicted sample. Its goal is that. Okay, so example for that is, for example, if you are if we want to sample from a linear Gaussian model with the parameters as follows: the mu, sigma, Gaussian, then if you perform Box-Moller transformation from a linear hypermodel, which is mu plus a c times x, then you will get a sample from x transpose mu and x a transpose x. If the algorithm can find the factor such that a transpose equal to the posterior, this kind of covariance sigma that measures the uncertainty about the model, then we can say that this linear hypermodel actually gives the predicted posterior sample according to this x. And also the randomness comes from the index. Okay, so the key is that we provide an incremental mechanism provably on A such that AA transpose is equal to the posterior covariance sigma given the dataset, history dataset. So this is our key contribution, that there's no previous work has any rigorous justification or any insight on such mechanism. Okay. Ensemble sampling is a special case. I will skip this page due to limited time. So for deep RL or GPT-based uncertainty exploration, we take such a last layer linear hypermodel that the hypermodel takes the index as input and output a parameter of last layer, and then it will process the input and output the value. Okay, and this part involving random index will measure the degree of uncertainty. If you sample different index, disagreement will measure such degree of uncertainty according to different indices. Okay, so this is our goal for this kind of model. And how do we update such model? It's very simple. Okay, and for state action function is similar, and it's just output a dimensional value that's similar in the previous page. Okay, so it is the update. The algorithm itself is similar in terms of double DQN. The only difference is the line 4 and line 9. Okay, line 4, each episode is sampled and indexed from the reference distribution, and also for line 7, it would take the greedy action according to the randomized value function. The randomness comes from the index. And in DQN, it takes the ipsum greedy. Here, our HyperAgent do not use any ipsum greedy, but instead we use greedy action according to the randomized value function. And in the line 9, we sample a random vector that will be useful for quantified uncertainty in an incremental way. We don't resample this perturbation for history data set. Instead, it is an incremental sampling process. So this makes our algorithm can be incrementally updated. The incremental I emphasize many times because it's very essential to achieve logarithmic per step computation. So the update rule is according to the objective based on TD error. The only difference is to the DQ1 is that there is a perturbation error here, and also our value function is determined by additional random index. Okay, so other things is the same as DQ1, and also we update the value, main value, and also the target value in the same way as DQ1 by mini batch SGD according to the objective function in TD error. And also for the contextual bandit case to involve this natural language, for example, in content moderation environments, we augment the GPT backbone with our hypermodel to a reward model, uncertainty-aware reward model, and then it will work very well in the online automatic content moderation problem, just as I mentioned in the beginning. Okay. And the algorithm is a contextual way, so we don't need the target value as mentioned previously. So everything else is the same. Okay. So how it works? It actually, we can prove some results by fixed feature mapping in one hot vector or some linear fixed feature mappings. So in the practical algorithm with deep neural nets or deep GPT, the feature part, for example, in GPT backbone, it allows to fine tuning such features. But in theory, the only difference from the algorithm side is we fix such feature mapping, and everything else in the algorithm are the same in the practice. So this is a bridging work between theory and practice. So we find that there's some component in the HyperAgent can represent the uncertainty in an incremental way that uses the perturbation random vector incrementally update that by the computation complexity with the dimension of this perturbation vector, that is m. The per step computation is proportional to m, and we prove that in tabular case and also in linear case, their m is proportional to log over the number of episodes or the number of time steps. So this is the key lemma that provides logarithmic computation. And then we can say this is an incremental uncertainty estimation in a very fast way because it's logarithmic in terms of t or k. And it approximates this posterior variance. In tabular case, it is essentially the inverse proportion to the counts of the assay. And in the linear case, there is a posterior covariance matrix. You can find it in our paper, so I'm not going into the detail here. So the HyperAgent algorithm also induces a stochastic Bellman operator that backpropagate the noise, the kind of randomized bonus into the initial state. For example, here, if this state action space is visited very less, then the noise is proportional to 1 over n is the count. So this noise is large, and then with the objective defined by HyperAgent, this uncertainty or the noise will be backpropagated into the initial state, then it incentivizes the deep exploration behavior. Okay, and also for contextual bandit problem is similarly, contextual bandit do not need exploration, but it needs uncertainty quantification. Is also can be represented as a approximation of the posterior variance, and then in such a way we can incentivize exploration in contextual bandit too. So basically, deep HyperAgent can incentivize deep exploration for reinforcement learning, and also it will incentivize this uncertainty-based exploration to acquire uncertain information that will improve the future capability of the agent, for example, in content moderation systems. That is the essential mechanism to improve data efficiency. Okay, data efficiency is very important in this kind of applications. The difficulty behind the mathematical analysis is due to the sequential dependence. And we develop new tools in martingale theory to handle such sequential dependence. And please refer to the paper for the detail. And this is a very interesting, I think, maybe it can be applied for other problems. And we have some new constructions of stopped martingales, vector martingales. And this is the theorem. I'm not going into detail. And to summary, we provide a simple, efficient, and scalable reinforcement algorithms that depends on fast incremental uncertainty estimation for posteriors. And it works well in concurrently significant applications, for example, content moderation, when the human feedback is expensive, or the limit is the human reviewer in the content moderation system is limited. And also this kind of decision-making process is safety critical. So the HyperAgent can work well there to solve this data efficiency issue or the feedback labeling issue. Okay. And we bridge the theory and practice by proving logarithmic computation complexity and sublinear regret bound matching the best known randomized exploration algorithms such as LSVI or Thompson sampling in respectively in deep RL and contextual band, linear contextual band. So you can take a picture or scan this QR code for more information. Thank you for listening. Thank you.